Hello students. Today we're going to look at modeling with exponential functions. And so we're going to look at a couple of real-world situations that are modeled off of exponential functions. Let's look at the first one. A population that experiences exponential growth increases according to the model n of t equals n naught times e to the rt power, where n of t is the population at a time t, n naught is the initial population, so at time 0, r is the relative growth rate expressed as a proportion of the population, or a percent, and t is time. Now, population growth is not always exponential, but there are many situations where it is. When bacteria is grown in a culture, oftentimes it is exponential. When a virus spreads, oftentimes it is exponential. However, there are often situations that stop exponential growth, like the bacteria running out of space or running out of food, or the coronavirus, which was spreading at exponential rates, but once people started to socially distance, to wear masks, to stay home, things like that, of course, it didn't continue growing exponentially forever. So not all populations grow exponentially, and some of them only grow exponentially for a certain amount of time. But we're going to be just looking at examples where we do have exponential growth. And I want to start by looking at an example that involves bacteria. The initial bacterium count in a culture is 300. A biologist later makes a sample count and discovers the relative rate of growth is 60% per hour. Find a function that models the number of bacteria after t hours. What is the estimated count after 10 hours? And when would we expect the number of bacteria to reach 5,000? Now, I want to make a quick note before we begin solving this problem. When we have a relative growth rate of 60% per hour, that doesn't mean that we will exactly have 60% more bacteria after an hour. If we look at the formula, this looks very similar to the formula for continuously compounded interest. That was A equals P times e to the RT. And we knew that when we compound interest continuously, we end up with more than the interest rate as far as interest goes at the end of the hour. So it actually ends up giving us a little bit more than 60% growth, because at the beginning of the hour, we might start with a certain number of bacteria, but after the first few minutes, it starts to increase, and the more bacteria there are, the faster it's going to grow. And so it's not that we're going to have exactly 60% more after an hour. We actually end up with a little bit more than that. But this is just how relative rates of growth go. Let's take a look at the problem now. We want to find a function that models the number of bacteria after t hours. So in this case, we have n of t equals, and if we look at the formula, we've got n naught, which is the initial population, and the biologist has seen that that was 300, times e to the rt. So we have e to the r, and here the relative growth rate is 60%, so that's 0.6, and then times t, and in this case t is measured in hours because the relative growth rate was per hour. So this is a function that models the number of bacteria that we can expect after t hours. So this is the answer to the first question in this problem. Next, we want to know what is the estimated count after 10 hours. In this case, we just have to evaluate this function at 10. So we have 300 e to the 0.6 times 10. Now 0.6 times 10 is just 6. So this will be 300 times e to the 6th power. And if we get an approximation for this, this is approximately equal to 121,029 bacteria, which is a huge number, but with such a large relative growth rate, we will end up with many, many, many bacteria. I mean, we're not quite doubling per hour, but if we start off with 300 and we're almost doubling every hour and we let it go for 10 hours, we're going to have many, many more bacteria, on the order of 100,000 bacteria. Let's take a look at the third part of this problem. When would we expect the number of bacteria to reach 5,000? Here, instead of substituting in a value for the time and trying to find the number of bacteria, we're told what the number of bacteria is, and we need to figure out the time. So in this case, 5,000 represents our n of t. So 5,000 equals 300e to the 0.6 t. We want to get this exponential expression alone, so we divide both sides by 300. When we do that on the left, this reduces to 50 thirds. So 50 thirds equals e to the 0.6 t. And if we write this in logarithmic form instead of exponential form, this becomes the natural log, because it's base e, of 50 over 3 equals 0.6 t. And to solve for t, we divide both sides by 0.6. So we end up with the natural log of 50 thirds all over 0.6, which is our exact answer, but we can get an approximation here. And we end up with an approximation of 4.689. And so we can round this to the nearest tenth. So let's say about 4.7 hours before the bacteria grow from 300 to 5,000. It's interesting, now that we've studied exponential equations and logarithmic equations, we can convert back and forth between exponential form and logarithmic form, and this allows us to solve for different variables in the equation. We can solve for n naught, we can solve for n of t, we can solve for the rate, we can solve for the time. At this point, we are mathematically advanced enough that if we have all of the variables but one, no matter which variable we're missing, we should be able to solve for it.